as some of you might remember from last year's presentation that I delivered, we have a trainee program where trainees try to learn on as much practical way as possible renewable energies. And Hakan and Doriet have been here, I think it was a year and a half ago, more or less. And they now graduated, and they actually graduated taking the project they started in Folke Center, which was optimizing a blade of a wind turbine, and turning into their bachelor project. I can see you're both here. I don't know who is going to start, how you're going to make the presentation, but now the floor is yours. Welcome.
Thank you.
Welcome back.
Thank you. It's an honor for us to be here. Thank you inviting us for speaking about our project. Okay.
Hello. Hi.
Oh, nice, Dorit. Dorit was having trouble with his audio. I can see he fixed it now. Okay. During our internship at Folk Center around 2 years ago, we picked a project called Make Your Own Small Wind Turbine. At that time, we didn't know anything about wind turbine and wind energy because we also didn't learn it in the university. Then in the Folk Center, we make research, and we got help from people at Folk Center. We took courses, like online courses. And then when we learned about how to make a wind turbine, then we said, okay, it's not enough. We need to do some research and development. And then we found that the noise is an issue, and also noise is also affecting the efficiency of the wind turbine blades. Yeah, that's why we made the research and development about the noise for the wind turbine blades. Okay. Next, please, do it. Okay, this was the our final prototype, which we made by our hands from wood, and we were testing this on the test field at the Folk Center. Next, please. Okay, we would like to show you a few photos, like how we did it by hand. Here, first of course we started to designing in 3D CAD Inventor, and then we draw it on a plate, like raw material, and then yeah, we were removing most of the materials. Here you can see on the raw material, we draw the lines, we measured everything precisely, as precise as possible. Next, please. And yeah, here another photo. One is almost finished, and the other one is we didn't touch it yet. Next one, please. Okay, we use different kind of machines, like sand machine, to give it the shape better. Next one. Yeah, and we were also using hand sandpapers. Next one. And yeah, we checked the blades, the leading edge, especially if the blades were the same or precise. We found some mistakes. We corrected them again. Next one. And yeah, we coated the blades with epoxy with 5 layers to give them waterproof and to give them more strength. Next one. Yeah, at the end, it's quite funny because at the end we measured the total weight of 2 blades, and I don't know if you can see it, but both of them are exactly on the same weight. That was quite awesome. Next one. Yeah, there was one wind turbine there, which was also made by hand. we removed the rotors and replaced our blades there. Next one. Here, a short video of the blades. And there, when we were measuring the rotor efficiency after the calculations we made, but of course it was uncontrollable. It was not able to control the environment. But roughly, we got a 55% rotor efficiency. It was really high for two-bladed wind turbines. Next one. Yeah, here we can see the CP, coefficient of performance of the wind turbine blades. If you look two-bladed rotors, the maximum is 45%. And okay, in the calculations, we took some small consumptions. Even though, let's say, there's an error, I can say that it's at least 50% efficiency we achieved with those two-bladed wind turbine blades. Next, please. Yeah, then we took this into our bachelor project, and the noise is a real important issue. We also found some complaints from Siemens, and they say that numerous complaints have been made, and it can be annoying to sleeping disturbance, or even some people had health problems. That's why we wanted to work with this noise issue of the wind turbine blades. Here, Dorrit will talk. Yeah.
Hello, hi. Do you hear me clearly? Do you hear me?
Yes.
Yes.
Yes. Yeah. Hi. And here I want to explain a short explanation about from where we get the noise. And we can see from this experiment that the noise come from the end of the plates. And here the experiment put a mic here and sensor, and we can see that the red color is the high noise we get it from the plates. And how the noise can come from, and it is the air come turbulent the turbulent boundary, and will generate in the trailing edge vertex, and vertex will make the noise. As I mentioned before, that the tip vortex is the highest noise, and the noise depends on the trailing edge, and of course it's depend of the angle of attack. And there is this is of course a problem of the noise. It's a problem for the turbine plate, wind turbine. And there's many of existing solution. The first one is about design the plates, but the solution that's now it's used, it's after design there is a serration, which is this, and it's from Siemens, and improved by Siemens, and it will reduce the vortex and will reduce the turbulent number. And there's a campus technology which put campus here between the triangle or between the serration here, and it will also reduce the turbulent boundary. And there is a special coating which it's riblet coating which gets from the shark, and it's reduced 5 dp, and it is you can notice that serration reduce 7 dp, and the riblet coating it reduced 5 dB, and the compass technology reduced 2 dB max. All of the number are max. And you can speak, Hakan, here about Twitch, yeah.
Yeah, yeah. When we were looking into the noise solutions and already existing, we also look into other sectors, like rather than wind turbine industry. We found that in helicopter company called Airbus, they were also working on this noise issues, and they, as you can see, the blades is a little bit curved at the end. If you come to next slide to it, yeah, and they were doing different experiments as well. With they made different blade designs, different shape. They were testing them, which one is best, and they found one of the curved ones best. It was reducing 5 EPNdB, and but they found that also the structure was quite weak. But then they improved the structure of the tip section, so it was suitable for flying in the helicopter, and they are using this in their helicopters right now. Next one. Okay, here we can see a clear photo of our design and a normal conventional straight wind turbine blade. But why we designed this one is because we also saw in other people like in the helicopters, but we came with this design from nature, especially from birds. And why birds? Because birds are dealing with aerodynamics for thousands of years. They have their wing and size differently compatible with their environments. Each of them have a different wingspan and sizes, but we need to find a suitable one for our design. And we pick a bird which lives in ocean, and it was albatross. And the interesting thing is that their wingspan is up to 3.5 meters. And the blade we made was one single blade was 1.2 meter. So total is 2.4 meters total wingspan. And they're known as gliders. They spend their life, most of the life in the ocean. And since they're known as gliders, it must tell us something, like they can glide in the air for a long time. So that means that they eliminate most of the vortexes, the air resistance. So when you also eliminate those issues, then it should also make less noise. And then we make our designs in Inventor like that, one with straight blade. We also tried with blue edge blade design, like we try to make similar to that one, but in the further slides we will not talk about that one. We will only compare conventional and the curved tip blade design we made. They are at the same size. I need to mention the same diameter. Yeah. To it now, he will talk.
Yeah, and you mean the same size? The same size is different. It's a curved.
No, I meant the same diameter.
Yeah, and it was our project, our final project in university. So we print our plates, which it's straight and blue edge and curved plates. We printed on 3D printer, and after that we ensure that it's the same our plate, it's our turbine, it's two plates, so we ensure that it's perfect. And we make our simple test, simple lab to get to know if it is which is better, and to know more about curved and straight plates. And the first test was about we about to calculate to know how much noise we have. So we bring voltmeter, mounting bracket, and dB application to measure the noise by mobile, and our three type of plates. As Hakan said, that's we have three type of plate, but to don't confuse you, we here explain only about two plates, the straight one and the curved one. We don't want to speak about edge, blue edge. And as a result, what we did here, that's we let the plates move, and we calculate, we put the microphone here, and there is here plates, but here is not shown because it's very fast. So the tip of the plate here will get the max noise. So we will have how much dB we have. So after calculation, there is here how many volt, and here how many noise. So start at 1 volt, and we finish at 6 volts. And here we can notice that the straight plates has more noise from the curved plates, especially in when we in 2 volts. The different it's less this 14% less than the straight plates, which is good. And after that, we make power consumption the same tools, but we want to know how much every plates consume. And also there is a volt here, and there is a power here. And when the difference here, we can see that's also the straight plates use here more power more than our design plates. And here in the 4 volt, there is a gap like 29% less than the straight plates, which also very good. And we want to make how generate the power, and we use it another tools. There is here put a van here, and the van there's a distance put the turbine here, or small turbine here, and the voltmeter device, and the van with distance. The first test it's for example 10 centimeter. The second test is 20 centimeter, which will get our turbine will get different wind speeds. And we have anemometer, and we use our plates. And here we want to show you only two distance. The fan far away from our router was 15 centimeter and 30 centimeter. Of course, everyone has different wind speed. We can as here it's volt, the volt for the diagram, and here it is it's a time, and we can see that the curved one, the orange one is the curved one. It's our design, and it's a start from 2.5 almost, and the straight one starts 3.5 second. So the curved one starts generate electricity. It's just generate or started starts electricity from need before the curved one. And if you also we make the van far away more than 13 centimeter, and also we have a very good result. That's our design started from 2.5 seconds, and the straight one started from 6 seconds, which is better. Our curved it's better, and the resist of the curved is it's by experiment it's better than the straight. And after that we analyze it by ANSYS, and as calculation here, that we can see the straight place design for max von Mises stress is the best, and it's logically because it's straight, and maybe here there's thicker than the curved, and the curved plates is 15, and if we compare, it's okay, because our calculation, it's the number must be under 30 megapascal. So it is good to work, and it's okay if we compare with another plates. As a conclusion, we are so proud for that we succeed to have a very good result, and to decrease the noise and increase the efficiency. And we want to develop it. Maybe it's as we can develop it by making achievement and optimization design shape using fluid design. And we can improve of test corrosion, improving of testing, corrosion evaluation, and maybe structure optimization. And we can combining with existing solution, which I spoke before, serration and coating and comps, we can put it on the plates, so maybe will be reduce the noise more. Thank you very much, and I was very happy to present this presentation, and any question we are ready to answer.
Thank you, Dorit and Hakan. Very interesting project indeed. Is there any question from the audience? From the digital audience? Well, if it is, then you can always write in the chat. Oh, yeah, there is one. No,
Thank you.
Okay. So thank you very much. If you have any question, you can always ask them to them as well. So now I would suggest to have a 10 minutes break. We are running a little behind the schedule, but we just need to set up a couple of presentations coming in now. And then the next presentation will be a physical presentation from here, from Otto Rank. So we see each other in 10 minutes. It should be 10:30 our time.
I would like to thank you, Daniel, to get us the opportunity to explain our project, and thank you for you and for Folk Center.